Greetings again. So, welcome back. So, we're going to move on to term three. Okay. So, today we're going to look at forces and Newton's laws. So, we're going to look at forces and Newton's laws. Forces and Newton's laws. Um, so, let me write down a list of formula. So, we have the weight, which is equal to mg. So it's mass multiplied by the gravitational acceleration. So now here you can say weight, or you can say Fg, force of gravity. Okay. And then what's next? We have Newton's second law, which says the net force acting on an object is equal to the mass of that object and then multiplied by the acceleration. Okay. And then what else do we have? Um, we have Newton's law of universal gravitation, which says F equals to G, which is the universal gravitational constant, M1 and M2, and then divided by the distance between the two objects. Okay, so this is the square of the distance between the two objects. What else do we have? So we can find G here, which is the gravitational constant on the surface of the planet. So we say G, and then we take the mass of that planet and we divide by the radius squared of the object. Okay. So and then the other ones, the other ones here we have. So we have the one for static friction. Okay. So Fs max. So this is the maximum static friction. It's going to be equal to the coefficient here of static friction multiplied by the normal force. Then we have kinetic friction. Kinetic friction here, which is going to be the coefficient of kinetic friction multiplied by the normal force. Okay, so let me try to write down the meaning of the symbols here. So this is what we're going to use for this topic of forces and Newton's laws. Okay, so you will find these on the formula sheet, and you will find some more. Okay, so now let me give you, you also have um, you also have the components of gravity. So the parallel component, which is equal to mg, then sine theta. Theta here, theta is the angle of inclination. So this is for objects that are on incline, okay? And then you have FG perpendicular, so this is the perpendicular component of the gravitational force. And then it's equal to mg cos theta. Again, the theta here is an angle of inclination, okay? So now, these two, you will not find these two on a formula sheet, okay? They are not given. So you should know these two by heart. You will not get them formula sheet. So again, what are the meaning of the symbols here? Let's write them down. Okay. Oops. So like I said, these two, the last two are not found on a formula sheet. So you have to know that these two by heart. They are required, although you don't find them on the formula sheet. So, okay. What do these things mean? Let us begin with W here. So it can be W. So it can be W or FG. So this is weight. This is weight or force of gravity. Force of gravity. Force of gravity, and the unit here, the unit of measurement is Newton. Okay. And then M. M is the mass. Mass of an object. Mass of an object. And it is measured in kgs. And then F net. This is the net force. The net force acting on an object. Is the net force. And it's measured in newtons. The G and then the small letter G. And then we also have A. Small letter G is gravitational constant. So in a majority of the times, it is 9.8. So it is 9.8 on Earth, okay? It changes if you go to another planet. So the 9.8, okay, is on Earth. Is on Earth. Okay, it's not the same if you move on to other planets. Like for example, if it's on the moon, it won't be 9.8, it will change into something else. Okay. And then A here is the acceleration. A is the acceleration, and the acceleration is measured in meters per second square. Okay. And then we have and after that we have F, which is, then also we have G, capital letter G. Then we also have R. Okay. Um, then we have F. So F is the force here. Okay. So in this case, so F is the force. So F is the force. And then in this case, it is between the two objects, the two masses. Okay. It's between the two masses. So F between two masses, because it is associated with M1 and M2. And then the unit of measurement here is Newton. And then the capital letter G. The capital letter G here is, this is the universal gravitational constant. Gravitational constant. So this is a constant that is the same. It is the same everywhere in the universe. It doesn't change. Gravitational constant. So it has the same value everywhere. So it's 6.67. And then multiply by 10, negative 11. Then the R here This could be radius. So it could be two things, okay? If it's between the two objects, okay, let me use the distance, okay? So this is one, this one is the what? Is the distance between centers, distance between centers, distance between centers of two planets. Distance here, okay, between centers of two planets. So it could be planet or it could be object. And it should be measured in meters. Okay. Okay, this is D distance. So if it's used, if that R here is used between two objects, then it is distance. But if it's one object like that, it is a radius. Okay. It is a radius, and the unit of measurement is the same. So it will also be in meters here. Just as the unit of measurement is the same for force and for gravity, gravitational constant here. So now, what happens here? Then the next thing is the capital letter M, okay? So the capital letter M here, to make a distinction, okay? What does it mean? So here, the capital letter M here in many cases is mass of a planet. So it's used to show the mass of a planet. And it's also in kgs. It's also measured in kgs. And then we go to the Fs max, which is the maximum static friction. Then we go to kinetic friction, and we go to the coefficient, the two coefficients. So for static and for kinetic friction. So it's gonna be static and kinetic friction. Okay. And then there is also the capital letter N, which is the normal force. Okay. So the Fs max is maximum, and then K here is kinetic friction. The kinetic friction and is measured in newtons. Fs max is maximum maximum static friction. Maximum static friction. Or you can say frictional force. It's not this. It's not. This is kinetic friction and maximum static friction. So you can say maximum static frictional force. You can say kinetic frictional force. Then this thing over here is not, this is not an English letter. So it looks like a U, but it's not. So this is the coefficient. It's the coefficient here. So it's the coefficient in both cases. Coefficient of static friction and then coefficient of kinetic friction. Coefficient of kinetic friction. And then, so for the coefficient here, there is no unit of measurement. It's just a number, okay? It's just a number. So both of the coefficients don't have a unit of measurement. It's just a number that is used, okay? And then the N here is the normal force. So the capital letter is the normal force. The normal force here and the unit of measurement is M, is newtons. Okay? And then what about the others? So, okay, FG parallel and FG perpendicular. Okay, so there is FG parallel, and then there is FG perpendicular. And then there is theta. And then there is so this is a component of gravity. Okay, so this is a parallel. So two lines here. It's parallel. Then this is perpendicular. Perpendicular. Parallel component of gravity. Perpendicular component of gravity. So this is the perpendicular component here of gravity. And they are both measured in Newton. So you have newtons here. You also have newtons. It's the unit of measurement. And then this is an angle. This is an angle of inclination. This is an angle of inclination. So is what? It's in degrees. It's measured in degrees. So that is this is a list of the symbols here, what they mean. So I wrote them down here so you can see, you can make reference to, because this is a list of formulas. So like I said, sometimes the weight can be, they can call it force of gravity, or they can say gravitational force. So this is over here is a very extensive list of the formula. This is a list of formula that we're going to use in for this topic. Okay. So the other thing that I want to talk about is the normal force. Okay. Because the normal force is not the same, isn't it? It depends on the situation. Okay. So now there is a lot of different formulas. So there's a list. It depends on the situation. So let me do it here. Let me try to do it this side. The normal force. Okay. How do we calculate the normal force? It depends on the situation. The formula is not the same. So, okay. Let's say we have a horizontal surface. We have a horizontal surface and we have an object. Okay? We have an object on the surface. This object has a mass m. Okay. And then we can have another situation here. So this is just an object. So in this case, the normal force will be calculated as mg. So the normal force in this case is equal to the weight. Okay. Now let's say you have another horizontal surface here. You have another horizontal surface. So we have an m here. And then in this case, there is a force. Then we can say that the force is acting at an angle here. Let's make a dotted line here. And then we can call this angle alpha. So the angle is acting horizontally upwards like this. So in this case, and it's not the same as if the object is acting horizontally downwards. So you can have another case whereby, again, you have a horizontal surface like that, and then you have the same force So we have an object with mass m, and then we have the same force that is acting horizontally downwards. And then we have alpha, yes. And then we have a force F. So the normal force in each of these cases. So in this case, the normal force will be equal to, okay, the normal force. So it's not the same. So if it's going up, it's not the same as going down on it. So the normal force in this case would be mg, Even here, you would have mg. But then if it's going up, it's going to be minus, okay, horizontally up and diagonally up like that. And then if there's a diagonal movement downwards, it's going to be plus. We add the component here. So we're going to minus the horizontal, the vertical component, I meant to say. So it's going to be F sine alpha. And then in this case, it's going to be plus F sine alpha. So now, if the force is acting diagonally like this, if it's going up is minus, if it's going down is plus, we have to subtract the vertical component over here, okay? So what happens if the force is not diagonal, is horizontal like that? So if the force acting on an object, so you can have, again, you can have M here. And then we can see that the force that is acting on an object is not acting at an angle. It is acting horizontally like that. In that case, the normal force is just the same as the first object. So it's just mg. We don't add and we don't subtract anything. Okay? So now, and then in other cases, you can have a tension force that is going upwards. So again, this is still, it's a horizontal surface. Okay. So you have an object that is placed on a horizontal surface like this. Okay. And there is a tension that is going up, acting on an object. So you can have tension, and then, so in this case, the normal force is going to be equal to mg, and then minus the tension, or or you can have the tension going straight down. So you could still have an object on a horizontal surface like this, and then you have a tension that is applied to the object. In this case, the normal force is going to be mg plus tension. Okay, so guys, you should remember that there is the formula for normal force is not given. It's not given on the formula sheet. So you don't find anything for normal force in the formula sheet. So you should know these situations. Okay. And then now, let's say you had what? You had an object that was placed on an incline. Okay. Let's say you could have an inclined surface like this. So in this case, there's an angle of inclination. Okay. So in this case, there's an angle of inclination. So we can, it's theta. This is theta. And this is an object, mass m. So in this case, the normal force would be mg cos theta. Okay. And then this is just an object. There's no force that is acting on an object. So you could have another. So let's do the two cases here. Let's say you have an object that is on an incline. Okay. So if we have an object on an incline like that, so there are two situations here. Again, you have an object of mass m, and then there is an angle of inclination with the horizontal, and then there is also a force that is acting upwards. So to S that is acting diagonally like that. So to make a distinction here between the two angles, this one is theta and that one is alpha. So there's an object, there's a force here. And then you have another situation. You have another situation where you have theta, and then you have an object of mass m, and then now relative to the surface, the force is now moving diagonally in a is on the other side of the um, parallel line here. So now you have alpha below the line, not above the line. And then you still have the force F. So the normal force in each of these cases is not the same. Okay. So the normal force in this case is going to be still mg cos theta. Okay. Mg cos theta. But then we have to say minus F sine alpha. And then in this case is mg and then cos theta. And then plus F sine alpha. Okay. So that is the difference here. We take the parallel component of gravity. So it's either we're going to subtract or we're going to add depending on the side of the parallel line where the force is acting. Okay, so each of these cases should be considered carefully. So it's not, and again, I emphasize that in any of these cases, the formula for normal force is not given on the formula sheet. Okay, so you will not find these things on an information sheet on your question paper. Okay, so you should know how to calculate a normal force in each situation in the absence of the formula sheet. And again, just like the previous one, if the force is parallel to the surface, so and remember previously what we said, so you can have another situation here whereby there's an object of mass m, okay, and then there is that. So in this case, the force is acting parallel to the surface like that. So meaning there is no alpha. It's not acting at an angle diagonally. So the normal force is going to be, so this is the force F. So the normal force is going to be the same. It's going to be mg, and then it's going to be cos theta. The theta here is the angle of inclination. The alpha is the angle between the force and the surface. Okay? It's the force and the surface on which the object is placed. So this is what you use to calculate the normal force. So you could have a situation where the surface is horizontal like that. Okay, like this these 6 cases that I showed you here. Okay, whereby the surface is horizontal. It's a horizontal surface. Okay, then you could have other situations whereby the surface is inclined. So there's an inclination. So the surface is not a horizontal surface, it's an inclined surface. Okay? And you have to know how to calculate the normal force. And by the way, okay, like I said before, you will not find this on the, so you should know it. And you should know how to use it, okay? So yes, that's it for this lesson. So in lesson two on forces and Newton's laws, in lesson 2, I'm going to show you an example, okay, where we use the formula here, where we use the formula for normal force along with the others that I showed you first. Okay, so we're going to use all this formula in lesson 2. Okay, so I hope that was helpful, and I will see you in lesson 2. Cheers.